So when I go to the next slide, let me see. Yeah. So the Ohm's law basically defines the current in any resistance is related with how much biasing you apply, okay, and whatever is the value of the resistance in the circuit. It could be a single element or any combination of the elements, okay. And when we change the voltage, the current in the circuit changes, okay. And what we believe is the resistance remains the constant. And that is what is the Ohm's law. Basically, we call it as an ohmic device. But practically, when you apply biasing and when some current flows through any resistance, it gets heated up. Okay. And once it gets heated up, the value of the resistance changes. And therefore, the current also changes when you change the biasing. Okay. And we expect to have a non-linear behavior. The resistance is not constant. As we change the value of biasing, okay, how much voltage we apply, the current is not varying proportionality with the voltage. Okay, so that's the practical effect. So should we consider it as a quantum effect of measurement? Because without applying biasing, we cannot measure the value of the resistance. Even if I take a multimeter and try to measure the resistance, you are having certain biasing, which is coming from the multimeter battery. Then and only then we can measure the resistance. Okay. So in order to get a precise answer, I got a couple of valves and a multimeter and an electrical network to showcase you how do we do the quantitative measurements. For example, here I am having smaller valve, bigger valve, still bigger valve. So the size and the wattage which is available in the market, okay, they are different. For example, it's a 100-watt valve, it's a 60-watt valve, and it is a 15-watt valve. Okay, so right now 100-watt valve is connected. It is showing me a resistance around 40 ohm. It's not glowing. Okay, but if I connect another resistance or the smaller valve, the value of the resistance is very high, around 300 ohms. Okay, and we believe because when we connect this valve to the 220 volt AC mains, very little current it draws. Okay, so higher resistance is justified. All right, if we take a 60-watt valve, then the value of resistance is around 80 ohm. So from the market, we can buy variety of valve, and using multimeter, okay, we can check what is
Children,
the
please
value
do
of the.
not annotate.
Yeah, I don't know. Somebody has drawn this thing on the screen. Why it is coming? I have not drawn.
No,
Okay,
no, children are doing it.
children are doing it. Okay. See, when we try to estimate resistance of a 100-watt valve, okay, we use this formula, V square by P. Okay, using the Ohm's law, I equal to V upon R, and power is equal to voltage into current. Okay, so if we take voltage as 220 volt, all right.
Sir, you're not audible.
Hello.
हाँ, अभी आ रही है
Hello.
आवाज. अभी आ रही है.
Ari? Okay.
अब आ रही है. और
So,
विमल जी ये जो भी कर रहे हैं वो आपको तो पता चल रहा होगा, तो आप जरा उनको मीटिंग से हटा दीजिए अगर उनको यही काम करना है तो.
यस मैम, यस मैम.
हाँ, ये
हाँ ठीक है.
स्क्रैच क्या किया है?
हाँ जी, हाँ जी. तो विमल जी आप तो दिख रहा होगा ना कि कौन से बच्चे कर रहे हैं. ठीक है. ओके
because
ओके सर, प्लीज कंटिन्यू. यस.
yeah 220 volt के लिए if I estimate for 100 watt bulb, the resistance comes out to be 484 ohm. Okay. So this we can do it for different bulbs available in the market. For example, 100 watt or 60 watt or 40 watt, 25 watt and 15 watt. The measured resistance is very low for these values, 40 ohm to something like 300 ohm. And the estimated value using the formula which we normally teach comes out to be very large. Okay. For example, 100 watt 40 ohm is measured with a multimeter, but when we calculate, it comes out to be 484. All right. So, well, using the Ohm's law, what we understand is the resistance is coming, okay, because of the motion of electron, okay, and it gets hindered, all right. So when we apply different biasing, all right, so the heating effects comes in, all right, because of the conduction in material, and the resistance is changed. Okay. So in order to examine this, we are having such a device we can build ourselves. What we have is a AC mains we have. We can convert it into a DC using a bridge rectifier and connect a valve. Okay. So when we connect this circuit here, I will show you in operation and connect this valve. Then we can measure the voltage across the valve. And at the same time, I connect a very small resistance, 1 ohm. So whatever voltage comes across 1 ohm resistance, that gives me the value of current in the circuit. So I know the voltage, and I know this voltage again gives you the current, and ratio of these two gives me the value of the resistance. Okay.
Excuse
This
me,
is
sir.
the, yeah.
Sir,
Is it audible?
yes, sir.
Okay.
Sir, you showed us that the difference in the estimated and the uh,
Yes.
estimated current and the real current, estimated resistance and the real resistance. Why is there such a big difference? About 10 times.
Yes. So the 10 time difference comes because of the heating effect. Okay. When the current flows in this bulb, it gets heated up and the resistance changes. So when you measure the voltage here and voltage here, that gives you the value of the resistance. So this is the reason. Okay. RT equal to R0, 1 plus alpha T. Okay. I will demonstrate you just now. I have got a valve and I will connect and I will show you how it behaves.
Okay, sir.
Okay.
Yes,
So
sir.
this is a temperature dependence of resistance for tungsten alpha, and the value of the temperature comes out to be around 2400 K, okay, using this formula. And when we try to measure the voltages on this network and measure the current, then we get this sort of a behavior. As you increase the biasing, the value of the resistance of a bulb changes from 40 ohm to something like 484 ohm. So this we can quantitatively measure using the devices I will show you. Okay. Well, if you take a smaller bulb like a 10 watt bulb, which is available like scooter and motorcycle have got a very small bulb, indicator bulb, okay, which works at DC 12 volt only. Even the car indicator bulb is about 10 watt, So you can measure the voltage and you can also measure the current. And when you plot a graph between the value of the current and the voltage, okay, it shows this sort of behavior. So this behavior shows a non-ohmic behavior. It means the resistance of this bulb is changing when you apply current and the voltage. So VI relationship is never a straight line for a bulb. Okay. If you try to plot resistance versus the biasing voltage, then you get this sort of a behavior, which I showed you earlier when we have, the condition where AC bulb is used. Okay. There is no difference between the AC bulb or DC bulb in the form of resistance. Okay. It's only, it operates at 220 volt. Okay. So it's a thin wire. All right. And this is a thick wire. It operates at 12 volt. That is the basic difference. Okay. Now we can also think of having a bulb connected with the capacitor. Okay. So that some of the voltage, whatever we apply AC, goes to the bulb and some voltage goes to the capacitor. Okay. The capacitor has got a resistance, reactance we call it, which can be estimated using this formula. Okay. 1 upon omega into C, where omega is the angular frequency of AC mains. For 50 hertz, the value of omega comes out to be 314, and we can work out the value of the resistance, okay, or the reactance of 2.5 microfarad. It comes out to be about 1.2K or 1200 ohm. So if we connect a 40 watt bulb, as I showed you, the resistance, dynamic resistance, I call it, is about 1200 ohm. Okay, when it is glowing. So we can connect a capacitor along with the bulb so that when we apply 220 voltage, the voltage distribution should be equal. Okay, but it never happens. Okay. Hello. So we can show you this kind of arrangement, bulb and a
Excuse
capacitor.
me, sir.
Yes.
Sir, can you explain the capacitor again?
Yeah. The capacitor and a bulb, when they are connected, so there will be a voltage distribution, AC voltage distribution. Okay, some voltage will appear over here and some voltage will appear over here. So it will not be 220 volt. Okay, I will show you, demonstrate you quickly. So these are the typical values which comes when the AC is connected. Okay, 220 volt is not equal to the voltage across the bulb or voltage across the capacitor. It shows a vector addition law. So VI square should be equal to VR square plus VC square. Okay. And this, we can play with different bulbs and get a feel that how the resistance of a bulb is changing, because these voltages we can measure with the help of multimeter. Okay. Right now, if I show you the arrangement, okay, or live situation, I got a multimeter, analog multimeter, I got a digital multimeter, okay, which gives you the value of the resistance or the voltage. All right. And I got bulb. For example, this is the bulb, and it shows me the value of the resistance around 39 or 40 ohm. Okay. But it's not glowing right now, 100 watt bulb. So if I connect this bulb to AC mains, Okay. This arrangement. And here I can measure the AC voltages, whatever I apply. Can you see my multimeter? This is the voltage which is coming.
Visible.
Can you, is it visible?
Visible.
Yes, sir.
Okay. So, right now there is no voltage going to the bulb. So when I switch on, the bulb glows. Okay. When I further increase the voltage, the power at the bulb changes. Okay. And this I can measure as a DC because I have converted my AC into DC using a bridge rectifier. Okay. So here is the DC which I am applying. So it has a direction, plus and minus. So when I have different voltages, okay, now it is stopped again. So I further start with the low voltage, and as I increase the voltage, the brightness changes. Okay, this shows there is a variation in the resistance of a bulb when you are glowing at
Excuse me, sir.
different voltages. Okay,
Excuse me,
and
sir.
yeah,
Sir, why the color of the bulb changes when we change the voltage or the power?
in fact, when we change the voltage or the power, the temperature of the filament is changing. Initially, it is a low voltage, so it looks reddish. Okay. The filament is reddish or orange. But when we increase the voltage, the temperature changes and it becomes a white, higher and higher temperature. Okay. So
Okay.
this is a,
Thank you, sir.
okay. So this is the intensity of the bulb we can vary. All right. And when you have a capacitor, I show you the arrangement. You can have a bulb and a capacitor. This is the capacitor which is available in the market. Okay, this is a 2.5 microfarad capacitor. So if I connect the bulb directly to the AC mains, it glows with the full power. Okay. But if the capacitor is connected, okay, it glows with the less power. So some voltage goes to the capacitor. Okay. And some voltage goes to the bulb. It means the resistance of the bulb is changing because of the voltage distribution. Okay. That is what you can identify and measure. So simply by measuring the voltage across this distribution network, we can estimate the value of the resistance of a bulb. Okay. I switch off this. So this is because of the RC distribution, and this is direct. So you can find the difference between the same bulb operating at DC or operating at AC. Okay. When it is operating with AC, the other bulb, this one shows a flickering, while this doesn't show the flickering. Okay. So I come back to my presentation. what I wanted to show you, that the bulb, there is a flow of electron only. But if you have a liquid metal, okay, and see the situation like this, there is a motion of an electron as well as motion of ion, okay, positive charge or negative charge. And you want to measure the resistance, what you do is apply some biasing, and that is how you measure the resistance. So there is a migration. But if you are having a liquid metal, okay, and place a magnet below, all right, then you can see that this positive terminal generates a dip, okay, because I just play this video for you. So when I connect this negative terminal, black, okay, what you are finding is there is a depression, as well as when the ions are flowing in magnetic field, they circulate around the electrode. Okay, so that shows the mass flow. Okay, the effect of mass of the ion. All right. So normally in the bulb, when the current flows, it's only the ion electron we talk about, but in liquids we can talk about the flow of positive ion also. Well, I'm trying to justify that even the bulb of a resistance is not exactly the classical phenomena. It is connected with the quantum science phenomena. That is what we like to talk about these days. So this is the century, okay, centenary year of quantum science we are celebrating, okay, due to the great physicist. And they say that even this light and the motion of the charges, okay, I mean the Raman effect takes place, which shows that the interaction of light with atoms and molecules, okay. So when there is a flow of charges, the temperature changes, okay, and then light is generated. So all that quantum phenomena is happening in the bulb, okay, and there is an energy exchange. You feel the heat as well as the light coming from the material, okay. So, well, when we do a simple experiment, that is also not simple, okay. Lot of thinking is involved behind why it is happening, how it is happening, and we can do some measurements, okay, we can demonstrate. And this is what I tried to do with the bulb, that even the bulb, okay, if we can measure the bulb at low temperature, resistance of a bulb, so a lot of science is coming with the low temperature measurement. If we can place this bulb in magnetic field, then we can talk about the magnetoresistance. So these are the interesting research area. We generate quantum dots. We talk about the charge quantization, even with the resistance measurement. When we measure the Hall effect, we talk about the quantum Hall effect, okay, how the electron hops within the material. We are having the devices like thermistor, okay, by by touching, we can change the temperature, the resistance of a material. So there are several oxides devices are available, used as a sensor, called thermistor. There are devices called LDR, light dependent resistance. When you shine with light, okay, the resistance changes. So even the simple resistance, okay, has got a lot of interesting science which the young students has to learn. All right, I can summarize the current, voltage, charge, and the flux, magnetic flux, through such a illustrative diagram. The resistance comes only with the current and the voltage, okay. And capacitor comes because of the charge and the distribution of charges, okay, around the surface or around. So that shows the capacitance. And the inductance comes where the magnetic flux is involved. Okay, when the current flows, the magnetic field is around. Okay, so there are several effects due to magnetic field. And these days we are talking about the memories or memistors, okay, where the flux and the charge, they are connected. Well, in nutshell, we have developed various low-cost equipment, okay, and some demonstration of fundamental concepts of science like the electrical measurement or the mechanical measurement or the wave measurement, heat effects. This we call it as the innovation hub science gallery. And what I have demonstrated is only the electrical resistance for you, okay? And it is interesting from the point of view of the modern science. There is a lot of happening of the interaction of atom and the electron, which is responsible for the resistance and the temperature dependence of the resistance. When you talk about the efficiency of a bulb, how much is the electrical power generated, how much is the thermal power generated, a lot of experimentation is supposed to be done. I mean, this bulb, we can put it in water and check how long it takes to get heated up. The water gets heated up. So that shows the thermal dissipation. At the same time, we can talk about how much intensity is coming, visible light, using some photometer we can measure. Okay. Then we can talk about the optical efficiency and thermal efficiency of these bulbs. Well, I just showcase a small innovation hub, how it looks like for all these children. It is there in Uttarakhand. So you learn fundamental science while playing with different components and the instruments available. All these instruments are designed and developed at IIPT RC6, which you can have opportunity to visit sometime, okay, one of the innovation hub, and play with all these things. This shows the atomic arrangement, how they are arranged, okay, a model. This shows the vibrating molecules, viscous dynamics, and so on. I'm sorry about the technical issue. Initially, I could not take up the demonstration with lot of measurements with multimeters, so that what I could have verified is basically you can do all these things here using the low-cost material available to you. So thank you. I like to stop and will be open for the questions or discussion if the students are comfortable.
Excuse me,
So
sir.
now we have a dedicated session for Q&A. You can ask your question.
Excuse me, sir.
Yes.
Sir, can you explain how the quantum Hall effect is used in the battery or sir, the circuits?
Well, I have not done the experiment, but I have read is that when you study the Hall effect, okay, you place your semiconductor sample in magnetic field. All right. You apply some biasing in one direction and you observe the induced voltage on the other direction. Okay. So when you change the voltage, the induced voltage, when you change the current in the sample, the induced voltage comes in these steps, okay, not increases gradually. Okay. Once it comes in steps, we say it is a quantum Hall effect. Okay, so many people have done theory on it and experimentally measured. So that's just what is a quantum Hall effect.
Thank you.
Okay.
Excuse me, sir. I have a question.
Yeah.
Sir, when we buy a bulb which is rated as 220 volts, 100-watt bulb,
Correct.
please let me know if my understanding is correct. If this 20-volt bulb, 100-watt bulb is connected to a 220-volt AC supply alone, that is in sync,
Alone.
then
Yes.
it gives out a power of 100 watt.
Correct. Yeah.
So if I use the formula R equals V square by P, I get the resistance as 484 ohms.
Correct.
Okay. Now,
Very correct.
yes. Now, if I let it glow for some time, due to heat, the filament is going to get hotter and hotter.
Hotter and hotter.
And with
Yes.
increase in temperature, RT is R naught 1 plus alpha T. So due to temperature rise, its resistance is also going to rise. Now, the rating, that is, if I were to measure the voltage and the power, what is nothing seems to be constant, isn't it? It is no longer a 220-volt bulb or a 100-watt bulb, but the supply is still 220-volt.
220-volt. Correct.
Because the bulb is it still 220-volt? And is the power emitted by the bulb again 100 watts because its resistance has changed? How do I know what is happening now?
Well, what I showed you is this sort of data for 100 bulb.
Yes.
Okay. When you go to 220,
yeah,
it almost stabilizes here. It comes in equilibrium.
Okay.
Between 200 to 220 volt or 240 volt, it comes in equilibrium.
Okay.
Okay. Because whatever power it is consuming, either it is radiating as a heat or as a light.
Okay.
So that balance is maintained from the formula V square by W. You get the value R.
So
Correct?
when you say equilibrium, you mean its temperature is not going to rise anymore. Am I right?
Yes, correct. Yeah. Temperature becomes stable, and whatever power it is consuming, it comes in equilibrium with the environment. Okay.
That means when the manufacturer prints that information on the bulb, the 220 volt, 100 watt,
Yes.
that value will be achieved only little later after switching the bulb on. Is my understanding?
Yes. After switching the bulb on. Okay. At initial stage, when the bulb is at different voltages, the value of the resistance gradually decreases, and when it is cooled, okay, it comes to the 40 room temperature.
So once that 220 volt value is achieved, after that, I think I have some difficulty in understanding. How is it that there is no temperature increase beyond that point?
Well,
It
what
is at
you will
equilibrium with
do
the
is,
surrounding.
what you can do is,
Yeah.
like this is the arrangement. Okay.
Yes.
You have got AC with a regulator which controls the AC to the bridge rectifier.
Yes.
Okay.
Yes.
And then we are having the bulb. All right.
Yes.
So we can maintain different voltage across this by controlling this, which I demonstrated you.
Yes. Yes.
Okay. From the setup.
Yes.
And what you can plan is put some coverage around. Okay. In order to change the equilibrium condition, whether you get variation in the current.
Okay.
Okay. You can put some blower on it. Okay. So that you take away some of the heat from here. All right.
Yeah.
Then you can check with the fan on and fan off. Is there a variation in the current?
Okay.
Okay.
Yes, sir. Yes.
So such experiment student can try out. All these data are from my own table, which I have shared with this setup.
So now this leads to another doubt. Instead of 100 watt, if it is a 60 watt bulb or a 40 watt bulb, also it will show a similar behavior. It will saturate at a certain voltage. Will that again be 220 watt? How do I know this?
Well, you see,
Yeah.
you can estimate
We are
the
conducting.
temperature using this formula.
Okay.
So the equilibrium temperature is different for different valve.
Okay.
Okay.
Huh.
So like the 15 watt valve maintains around 1600 degree Celsius only, while 100 watt valve maintains around 2500 degree Celsius. Okay. K, sorry.
Yeah.
Okay. So that's the basic difference between different wattage of valve. This is the temperature of the filament. Outside, it is almost surrounded with air. So there is a slight increase of temperature, something like 70, 80 degree, or even glass temperature goes to something like 200 degree. Okay, the surface of the glass. If we throw water, it may crack.
Yes.
Excuse me, sir.
Yes.
I have an unrelated question. Sir, why does light show dual nature in a double slit experiment?
Why
does light show the wave nature and the particle nature at the same time in the double slit experiment?
Well, in laboratory, when we do the experiment, okay, then we find only the wave nature, no particle nature. If you do the experiment with single photons, okay, then you don't look at the wave nature, but individual photons behavior one can identify. Okay. Normally, for example, 100 watt bulb, it emits about 10 to the power 15, 10 to the power 16 photons per second. That you can estimate how many photons a bulb is emitting. Okay. Using the formula NH is the energy taken by each photon and how much power you are giving. So, well, looking at the quantum particle, you have to really take a very low intense source. Okay. Microwatt.
Sir, that then you are saying that light is a wave, but waves require a medium to travel through.
Yes.
Sir, then how is light traveling through vacuum?
Well, light wave and sound wave, they are different. Okay. Light wave doesn't need medium, while the sound wave need a medium. Okay. The other difference are they are transverse and longitudinal. Light wave, we call it as an electromagnetic wave. Okay. Any source of light has got some vibrations of atoms or electrons, okay, which are responsible for emitting electric field or magnetic field around it. And that is what we call it as an electromagnetic radiation.
Sir,
Okay.
Sir, how good the how the better the electromagnetic waves are, the higher the speed will be.
How can you ask again, please?
Which means that if the electromagnetic waves are better, then the speed would be more.
Well, electromagnetic waves, they all travel with the speed of light, maximum speed.
Yes, sir.
Okay. It's only the sound waves which travel in different media with different velocity. Okay. All right.
Why light slows down and water? It slows down by about 25%.
Well, because of the refractive index. Okay. It slows down. All right. Because the ratio of the velocity in vacuum to the velocity in a medium is called the refractive index. Okay.
Okay, sir.
Yeah.
Excuse me,
Okay,
if
so
I may continue. Sir, this table that you are showing on the screen, I think I missed when you were explaining.
Oh,
Our estimated ohm is 484 ohms, but the measured is only 40. Same.
this is for 40,
Yeah. Why?
100 watt.
Yes.
For 60 watt, this is the measured value,
Yes.
and this is the estimated value.
Yeah. Why is there such a big difference, sir? Almost like 10%.
Yes.
More than that, but
Yeah. So this relationship is coming from the Ohm's law formula. Okay. V square by P.
yes.
Right?
Hmm.
So V square is always constant.
Yes.
Right?
Yes.
It's only the P which we are varying. So if you put 60,
Yeah.
then you get different value.
Yes.
Yeah. Okay. Or 40 or 50.
No, sir. My question was, why is there a difference between estimated and measured value?
Estimated and measured, you see, the measurement we are doing at room temperature. At this time, the bulb is not glowing.
Okay. Got it, sir.
Okay. The biasing is very little. All right. So here we say it's a effect of observation.
Okay.
Okay. When we apply biasing, more biasing, the current flows and it gets heated up.
Okay.
All right.
Thank you so much.
So these are the valves. Okay. This is 80 ohm, approximately it's a 60 watt valve. And if it is a 15 watt valve, we get around 300 ohm DC measurement. And if it is 100 watt, we get around 40. All right. And the relationship between the voltage and current, it is a non-linear. Okay. In certain range, when we talk about delta V by delta I, it's a linear, right? But in long range, it's a non-linear. Okay.
Yes, sir. Thank you so much.
Yeah. So, well, I hope I could answer some of the doubts of
Sir, I have
the
a question.
students and the teachers which are there. So by doing the experiment, simple experiment in the laboratory with the available devices, we can learn detail about the non-ohmic behavior of the valves. Okay, this is a non-ohmic behavior of the valve. All right. If we plot this curve with current versus the resistance, then you get this sort of behavior, which I showed you in my next graph. Is the current versus voltage or the resistance? This is the behavior. Okay. If I have the resistance versus voltage, then this comes. the shape comes like this, and it gets saturated, at certain voltage. That was one of the question. Okay. And in fact, this sort of experiment where student can learn that this is a not power consuming device, okay, which is responsible only to change the voltage across this resistance. Okay, the power is there only, V into I. This is a non-dissipative or ohmic loss is not there on this. So we can only control the voltage. Okay, so at different voltage, we can find out resistance of this valve. This is what I wanted to share and demonstrated. Okay, valve and a capacitor. One can do the experiment with valve and a choke, but we have to worry about the resistance of a choke. Okay, also along with the inductance. Here, the internal resistance is very small. It's only the capacitive reactance comes in. And one can verify this vector law, okay, the voltage ratio, because the input voltage, 220 volt, is not exactly equal to the voltage across C and voltage across R. It means they show the vector relationship. Okay, and that is what we can verify using this VI square is equal to VR square plus VC square. Simply, you square and add up, take a square root, then you get this value. Okay, with a good approximation. So you can play with different value of capacitors, okay, and find out how much is the voltage and corresponding resistance one can estimate with the voltage ratio. Okay, so simple experiment with deep learning. We talk about, as Verma sir says, that do simple experiment with available material with you, okay, and try to learn maximum out of that.
Sir, I have a question.
Yes, please.
Sir, how is the discharge tube non-ohmic?
How the discharge tube
non-ohmic.
Oh, okay, okay. You have seen the discharge tube somewhere?
Yes.
Okay.
Like I know about it, but I haven't. It's used in some devices, right?
Well, in discharge tube, what you have is two electrodes and some gases there.
Yes, sir.
Okay. So when you apply some biasing, ionization takes place.
Yes, and it conducts current then.
And the conduction starts. Okay. Yes. And when you change the biasing, the velocity of these ions changes. Okay.
Yes, sir.
And that gives me the non-ohmic behavior. All right.
Yes, sir.
Because the number of ions are fixed.
Yes, sir.
Okay. Initially, they are colliding, moving randomly. All right. So they are drifted only a few ions in a particular direction. So initially the current is low, but as you increase the biasing, current increases. And after that, it gets saturated because whatever is the density, that is limited. Okay. So there you get almost nonlinear behavior. In particular range of voltage, you get a linear behavior. All right.
Yes, sir. Thank you.
Okay. Any other question? I gave you references of some of the devices like LDR, light dependent resistance. Okay. That's a very low cost device. In 10, 20 rupees, you can get one. And the resistance of the device changes with the intensity of light. Okay. and you can play with the intensity of light, like in presence of bulb, we vary the power, the intensity changes, and we can do some experiment using the LDR. I also gave a reference of thermistor. Thermistor is also a low-cost device which is easily available, which is used for sensing the temperature, okay, in the low temperature range, like soldering iron tip, you like to measure the temperature, you can use this thermistor, okay. So when you switch on the soldering iron, how the temperature is growing, you can calibrate with the thermistor and do it experiment at low cost. Okay. Even the surface of bulb of different wattage have got different temperature that you can measure with the help of thermistor in place of touching. Okay. So again, using the resistance, you do some calibration and then use that calibrated value to find out the temperature. ओके, आज वर्मा साहब बाहर हैं, विमल जी?
Yes, sir. Yes, sir.
हाँ. So I think the session went well for almost 1 hour. Recording
Yes.
हो गई होगी,
Yes, sir.
so that we can get a feedback and some more questions will come. I will be happy to reply. And my present affiliation you can share with the students. Okay.
Yes.
At IIS School Jaipur, Vijay YK @gmail.com is my email address. Okay. And well, I hope the students might have enjoyed some discussion. Initially, it was technical problem, probably. Okay.
Yes, sir. So as we near to the conclusion of the today's webinar, I want to take a moment to thank you for attending this insightful webinar. Wow, that was an electrifying journey into the world of electrical resistance of the world. A huge thank you to everyone who made today's webinar a success, especially our esteemed guest speaker, Professor YK Vijay. Your insights on electrical resistance and non-ohmic behavior were truly mind-blowing. Professor Vijay's explanation on how bulb resistance changes with temperature was particularly fascinating. And it's a great reminder of the importance of considering material properties in electrical applications. We know some of you might have experienced technical glitch during the session. We apologies for any inconvenience it caused. Calling all science explorers, are you ready to dive deeper into the fascinating world of physics? The National Anveshika Experimental Skill Test NAEST 2024 registration is open now. Don't miss out on this exciting opportunity to test your skills and knowledge. Register today. NAEST isn't just a competition. It is an epic adventure. It's your chance to ignite your curiosity, test your problem-solving skills, and collaborate with other science enthusiasts. Imagine the possibilities, refine your skills, gain valuable experience, and maybe even contribute to the next big scientific breakthrough. So, are you ready to take a challenge? Gather your friends, spread the word and register for NAEST 2024 today. This is your chance to embark on the thrilling journey in the world of physics. A final round of applause for Professor YK Vijay. Thank you for sharing your knowledge and passion with us today. To all our participants, thank you for your engagement. And let's keep the scientific spirit alive and continue to inspire each other as we strive for excellence in the physics and beyond. See you the exciting path of scientific discovery. Thank you.
Thank you. It's all dedicated to great physicists, the quantum science. And we are celebrating it. And that is how we like to share with the simple experiments how they have given wonderful ideas. Okay.